So over to you, Savandi.
Thanks, Kate. So, okay. We're going to talk about evaluating a group of algorithms. So we've got so many algorithms for different problems. Say, for example, it's if it is about, like the standard classification problem, you want to differentiate sheep from cows or sunflowers from tulips, or, classify emails into spam or non-spam, or, find handwritten characters, all those things. So it's not a single algorithm. You've got so many different algorithms. And of course, there are so many different problems of the same problem category. So when we've got all these algorithms and all these problems, we know that from all the work that's been done in this area before, that no single algorithm is all powerful. This is the best for everything. That there is kind of no such thing. So this comes broadly under the no free lunch theorems, but so for different algorithms are better for different problems. So in these kind of cases, how do we evaluate the algorithms? Of course, we can take the on average performance, but if you say on average, this algorithm performs best, on average, this algorithm performs second best, and so on, we are going to miss strengths and weaknesses. So the thing that we're going to look at is how do we find the strengths and weaknesses when we have a portfolio of algorithms? So, and what we're doing in this, and of course, Kate's instance-based analysis work ties heavily with that question, with answering that question. We are trying to do a different way, which is using item response theory. And so I'll be talking a little bit about item response theory, and then how we map item response theory to algorithm evaluation, and then talk about new metrics and how we're going to reinterpret it, and also the strengths and weaknesses and some examples. So item response theory, these are a collection of models that is used in social sciences and psychometrics. So the idea is that there is an unobservable characteristic, and you have observed outcomes. Say for example, if you've got a racial prejudice or stress proneness or political inclinations, like a classic thing would be political inclinations, when you have to really think to know how left-winged or right-winged are you on the political spectrum. So it's not automatically that so maybe by answering some questions and things like that you would find but it is in there in us. So there's this intrinsic quality that cannot be measured, but you can have observed outcomes. That is, observed outcomes are more if you do a survey or something like that, the answers to the survey are the observed outcomes. So in education, we use IRT to find the discrimination and difficulty in test questions. So and also the ability of the participants, and you fit the IRT model and you can find these things. So of course, in an educational context, we like questions that can discriminate between students with different ability, rather than having all very difficult questions. I mean, as educators, we know we can make lots of difficult questions, but that's not going to give us anything. The questions that can differentiate between different abilities, students with different abilities, is what's better. And so how it generally works is, okay, you've got lots of students and they do these tests. So it can be any kind of test, multiple choice, or answers, long answers where you grade the test. But the input to the IRT model is a matrix like this. So you've got the questions and the students. So this matrix, these are the marks that the students get for those questions. After you mark them, you're going to put in the marks, and you fit the IRT model, and you get for each test question, you get how discriminative it is. And of course, you get the difficulty of the test questions as well. And then you get the ability of the participants, which is the latent trait, which is the hidden ability. So that's IRT in education. And in psychometrics, if you want to find out what is people, or what is the self-esteem of a person. So you have these surveys that you can do. And then this Rosenberg self-esteem scale has these kinds of statements. It has I feel I am a person of worth, and you strongly agree, neutral, disagree, strongly disagree, and then you take the original responses. So everyone does these surveys, and you take the responses. Of course, you don't have to mark them and then make another score from it, because there's no right or wrong. And then you fit the IRT model from the original responses. So the output in this case is the participant's self-esteem, and that's the hidden quality that you're trying to get. And of course, for each question, how discriminative it is and the difficulty of the test question. So in psychometric scenarios, mostly the hidden self-esteem, the hidden ability, the latent trait is of quite big interest, whereas in education scenario, you're more interested in the discrimination of the questions. Because say for example, you do say you do this exercise and you find the ability of the students is different from the total marks, in the sense there are certain students with higher abilities who've done more difficult questions, but you're not going to change the marks, say because of the model we've changed the marks. You're never going to do that, right? So it's more to tune the test paper that you would be using something like this. So in data science and machine learning, this is using IRT is a relatively new area of research. So the idea would be to find, say, if you're talking about a set of classifiers, what is the ability of the classifiers, or what is the discrimination difficulty of data sets? And this is what was done in this paper. That was in 2019, Item Response Theory in AI by Martinez, Pleman, et al. That paper, which appeared in Artificial Intelligence. And Kate presented this paper, and then this was kind of the I think there were some other papers, but this was the kind of the paper that came in this well-known journal linking IRT to all these things. Even though there was some other, when I look back, there are some other smaller papers in much less well-known journals talking about data science and IRT. But this was the big one that came. And what they do is precisely here, they're talking about the ability of classifiers and discrimination and difficulty of not of data sets, but of observations in a given data set. So to go through with this work, I just wanted to go through different IRT models, because there are many models as well. So there's a dichotomous model where the output, so it's like a multiple choice question. You've got, you have a true answer and the others are false, or can be true or false questions. So the equation that describes it is this one here. So Xij is the outcome or the score. So this is the mark. Even though it says outcome, that's the mark of examinee I for item J. So if you get 1, and the curve of getting 1 or 0 is given by this curve, and you have theta is the ability of the examinee, gamma is the guessing parameter, D is the difficulty parameter, and alpha is the discrimination for a given question J. I is the examinee. So here, theta is the x-axis. When the ability increases, then getting a higher score increases. Right, getting a high score increases, getting 1 for that question. And of course, there is a guessing parameter as well, because some questions are kind of easier to guess than others. And the slope here is the discrimination. That is, if the ability goes from one side to the other quickly, then you're going to tip over and get 1 for that question. Then, of course, there are polytomous IRT. So that is, you're not getting, your mark is not just 1 or 0. Your mark is, it can be a letter grade, A, B, C, D, E, or it can be like a score out of 5 or score out of 10, whatever, you know, so you can get different points. And again, theta is the ability. So here in this graph, if we look, we'll have, you know, for low values of ability, you're going to get the most probable outcome is this orange kind of curve, right? So that has the highest probability, and P1 is always less than P2. So P1 is like getting 1 mark, and P2 is like getting 2 marks, 3 marks, and so on. So you're most likely to get 1 mark for that. But if your ability is way over here, you're much more likely to get a much better mark. Like, and if your ability is somewhere in the middle, you're going to get, you know, a mark like that, right? So that's the polytomous case. And then you have the continuous case. So the continuous case is, you know, not actually continuous. It's like you have a lot more values, like say grades out of 100. So it is strictly speaking, it is discrete, but then, you know, you can have, you know, a lot more grades out of 100 with, if you mark with decimal places, whatnot. So then you can model it as a continuous thing. And then here, so for a given value of ability, you have a probability of curves here, just like the previous one. But then in this probability, you're much higher. If your ability is over here, you're much more likely to get a score somewhere there, which is the normalized score. So you know, but if your ability is low, you're going to get a score somewhere there. So those are broadly so it depends on the type of output. So if the output is binary, you can have dichotomous. If the output is discrete and like a small set, say 5 or 7 or something like that, you'll have polytomous. But if you have the output is 100 values, then you're going to have a continuous model. So when we are mapping algorithm evaluation to IRT, so it is like, how are we going to map? So because the original setup is, you know, people are doing something, like a person is doing a test. So you have this person doing something, and then you have this test, which is an inanimate object, and then you fit the IRT model. And then you get the item characteristics, that is like items are questions in the test, which is difficulty and discrimination, and then you get the ability of the people. And in traditional IRT, you have a lot more examinees than you have questions. So that's the thing. But when we are talking about algorithms and data set, who are the persons, or how are we going to map as persons? What are the test objects? That's the thing. So the standard setting that was done by Martinez Plimet, they mapped algorithms to persons because the algorithm is doing something, and the data set is inanimate, and then, you know, the data set is just there. So you have the data set as the items. So they had of course item difficulty and discrimination. So we can get data set difficulty and data set discrimination, and you get the ability of the algorithms. The thing is, though, with this, you're getting 2 IRT parameters for the data sets, and you're only getting one IRT parameter for the algorithm. So you're in a way evaluating the data sets more than the algorithms. So then we thought, okay, what if you flip it around, right? You know, if you can think of data sets acting on these algorithms, right? So these data sets come and, you know, because you write the code, who's acting on who. So if the data sets are acting on the algorithms, then you're thinking of data sets as people. And then the person ability, in the end, it gets translated to data set difficulty. That's what it gets translated to you after doing things. And then you have the item characteristics. Those are the algorithm stuff. The item difficulty gets translated to the algorithm difficulty limit. So that's the limit, that the highest limit that the algorithm can handle. And from the item discrimination, we get two things, the stability and the anomalousness indicator for the algorithms. So now we get two, well, actually three things, because we have the difficulty, stability, and anomalous indicator. So we get three parameters or metrics for the algorithms, and then of course one parameter for the data sets. So we have more on algorithms. And so if you look at this, what are these new parameters, right? So in IRT, the standard IRT theta I is the ability of examining I. So when theta increases, the probability of success or higher scores increase. So in our case, theta, so remember in the previous one, instead of a person, we have a data set. So theta is a parameter for the data set. So what is theta in terms of a data set? So when what increases would the score from a given classifier or an algorithm increase? When we get a more easier data set, then we'll have a higher score. So theta is actually the easiness of the data set. But when we did the easiness of the data set, and in the, when we submitted the paper the first time, then there were reviews like, it was difficult to understand with the easiness of the data set and the other things. It's so much more easier if you have the data set difficulty. So we made this new adjustment. Delta I is negative theta I, and delta I is the dataset difficulty score. That way, it's much more intuitive. So alpha J is, again, the discrimination of item J. Now, what are items? Items, so let's go back. Items here are algorithms, right? Items are algorithms. So alpha J is the slope is something to do with the algorithm. So if you have a very high, so when alpha is a slope. So when alpha increases, slope increases. But what would that mean? That would mean when you have a very high slope, so so in this case, this is still easiness values, right? When the easiness of the data set goes from one value to the other, there's a quick change, right? There's a quick change. So quickly, this algorithm works on a difficult problem, and then the algorithm works on a slightly easier problem, but there's a big change in the performance. So it's like lack of stability or robustness. So the higher the alpha, lower the stability or the robustness of the algorithms, because it will have very big fluctuations in terms of performance. So we made a new stability indicator or robustness indicator was 1 over absolute value of alpha J. So so a stable algorithm looks like this. So in the sense, when your theta increases, it doesn't really make much of a difference. Right. And in education scenarios, if you don't have a non-discriminative algorithm question, that would mean like a very easy question or a very difficult questions. And both of those wouldn't give us some information, right? But in algorithm evaluation, we want to know about those algorithms because they're pretty good algorithms. And then we have anomalous algorithms. Anomalous algorithms are so curves like this. So when I'm talking about the curves, I'm still referring to the the original curves. So I haven't flipped them. But when we're talking about the metrics later on, we will talk about the actual metrics. So in this one, when the ability increases of a student, the score drops down. And we know from practice there are questions like that. It's like, the question is worded in such a way that the student, like the good students, can overthink, whereas the weak students don't see that, don't see that big overthinking opening, and, they just do the quick thing and they get the marks. So in education, generally, if you've got negative discrimination algorithms, those questions are either discarded or they tell them to revise it. So they revise it to make positive discriminations. But we don't want to do that. We want to keep those algorithms, because we want to know, okay, what's with the, these algorithms are interesting. They're they're doing in an anomalous way. We want to know them. So anomalousness is the sign of this discrimination parameter, which gives the slope. So when you fit the IRT model, so we are doing a continuous model here, we are maximizing this expectation. And we made some changes to this expectation, very minor changes to this function, because we wanted to keep the anomalous algorithm. So we otherwise they didn't have the absolute values for the alphas and the gammas. So here alpha is the discrimination parameter for the jth algorithm, gamma is a scaling parameter so that the probability density function adds up to 1, beta is the difficulty parameter, and zij is the not the anomaly score, it is the performance score. Yes, that's a typo. And then you have this prior probabilities that you get. So then we from this matrix where you have these performances, we fit the model, and then we get algorithm metrics. We get the stability, and then we get the difficulty limit and the anomalous indicator. And then we get dataset metrics as well. We get all the difficulty scores of the datasets. That's what we get after we fit it. So now that I've talked about that part, I'm going to talk about an example. So this is the graph coloring algorithm that Kate and the team did from the 2014 paper. So they have 8 graph coloring algorithms, and the performance, there's a matrix. So the columns are each algorithms, and the rows correspond to each graph. Each row says how many colors did each algorithm use to color these graphs. So, and they have it on 6,000 odd graphs. So when you fit the model, this is what the pictures look like. And we immediately see that the bottom column, they're very stable algorithms. He and partial call, tabby call, and AND call, they're very, very stable algorithm. And from this table, we can see all of them have very high values. He specifically have a very high stability. These ones are not so stable because, they have those lightsabers going. And in the random greedy, it's kind of like very hazy, but you can see a little bit. And in this case, you don't have a single anomalous algorithm. All of the algorithms are normal. And even the difficulty limit, when we look, he can handle really difficult problems. Whereas then Tabucol can handle really difficult problems as well. And then if you look at this backtracking algorithm or the random greedy, they can't really handle that difficult problems. So we have so from these algorithms, and so each dot is a performance of a graph for a given algorithm. And so this is the performance. So 0 is not good performance, 1 is good performance. And then here we have the problem difficulty. And this is all the algorithms put together, but these are if you separate by different algorithms. And we see as the problems get more and more difficult, the performance generally drops. But then for he, it is like, really, there is a slight drop, but not so much. There is a lot of good performances here. In AND call, you have, like a shower kind of thing going like that. Random greedy, you have these things. So you see these patterns. Now, because we have these patterns, so we have this algorithm performance on the y-axis, and then we have the problem difficulty on the x-axis. So we can fit a model for the performance based on the problem difficulty. So previously we didn't have problem difficulty. We are getting problem difficulty from the IRT model. Right? We are getting problem difficulty from the IRT model. Using that problem difficulty, we can fit a model to the performance values. The performance values we always had. And well, you can fit any model, but we are using smoothing splines because you can visualize them. It's a 1D model, and and then you don't have to specify parameters. It's easy, so we're using, and it smooths the performance. So we're using that. So when you fit the smoothing splines to this performance, so this is now one step away from fitting the IRT model. You fit the IRT model, and then you get all the you get the problem difficulty parameters, and you have the problem performances, and then we fit the smoothing splines, and we get these curves for this particular problem. We see the purple curve is the random greedy curve. So for very easy algorithms, it's performing well, but then after that, it's the worst algorithm for the rest of them, right? And then, we have some of those curves on top, which is kind of hard to see what it exactly is on top. So when we have these smoothing splines, the obvious question that comes next is, now we can visualize the strengths and weaknesses of algorithms, because you have this ordered spectrum that is the latent rate, which is a problem difficulty. So on the problem difficulty domain, if a curve is on top, it is strong in that particular region. And if the curve is at the bottom, it is weak in that particular region. So then you can find the strengths. So how do we find the strengths? So just a little bit here, we first find this J star is the best algorithm for a given difficulty. So HJ star delta, here delta is the problem difficulty, and so that would give us the maximum of all the curves for that difficulty. And when we say for a given algorithm, J, the strength of that algorithm is when the parts of the problem space, so that's parts of the difficulty spectrum, where it is epsilon close to the best algorithm, where because J star delta is the best algorithm, and if the jth algorithm is close to that by epsilon, if it's very close to that, so epsilon is what we are defining. So if it is close to that by epsilon, then that algorithm is strong. If you set epsilon to 0, then you're getting only the best performances. Right. So, but you can have a little. So epsilon is the leeway that we are going to do. We are going to give when we are defining the strengths. And then weaknesses are similar as well. You're going to look at the bottom curve and then the curves that are closest to the bottom curve. So the strengths are the curves that are closest to the curve that is at the top at every point. So for this example, the graph coloring example, we have the strengths and weaknesses. We can visualize them on this problem difficulty space. And here we have epsilon 0 and epsilon 0.01. And, if you look at the weaknesses, you see the random greedy, which is the purple one, it's weak from that point, like from negative 1.5 onwards, it's weak from that on. But it has a strength for very easy algorithms, because easy is on the left and difficulty is on the right. So for very easy, it's good, but for everything else, don't choose it, right? And then if you look at the strengths, so this is the top two graphs are when epsilon is equal to 0. So that is why for every for every x coordinate, you only have one algorithm chosen. So we see this dark green algorithm, and that is HEA algorithm that's there for quite a bit. And then you have these other algorithms coming up as well. But if you give a little bit of epsilon to work with, you see that, there are a lot of algorithms are strong here. So these are relatively easy algorithms, relatively easy graphs to color. So that is, from around -1. So that part, right? A lot of algorithms can perform well. But when you get more to this side, you have either, for the difficult graphs, so from 1 to 2, so even though we can't really see this, we have the green algorithm, which is here, and then the pink one here and there, which is typical. So so you see, for difficult problems, he and typical are doing well, but for kind of easy problems, you have a lot of algorithms that can do well. And this red curve, ant colony, is doing well in the middle for this bit where actually around 0, ant colony is on top with the ant colony is on top there, and then there is no algorithm that performs well in that space apart from ant colony and he. So that also has kind of a unique pocket there. So we can visualize the strengths and the weaknesses by doing this, by fitting these splines. And then it goes to the next obvious step. We can use the strengths to select a portfolio of algorithms. Right? So because we know what are the algorithms that have strengths and what are the algorithms that are weak, so we can we can have a strong portfolio and a weak portfolio of algorithms. Of course, we call this whole framework IRT. IRT is for algorithm IRT, and then it comes from the Scottish word to guide. So we can have two algorithms, two portfolios. So if you look at, in this case, okay, for epsilon 0, what is a set of strong algorithms? Okay, these algorithms have strengths. Just let's make a portfolio of that. Or epsilon equals to 0.01. Well, everything gets chosen, but in here, one of the algorithms doesn't get chosen. So you can have the strong ones and the weak ones. And then, of course, you can use these algorithms, this portfolio of algorithms, and you can compare this portfolio with other portfolios as well. So when we compare it with other portfolios, we are looking at this metric called the performance deterioration metric. So if I is the problem, like, the graph coloring problem, for example, and P is a portfolio of algorithms, and if you have F is the full set of algorithms that you have, so the performance deterioration for that I instance using P is the best performance when you use the full set of algorithms minus the best performance when you use that particular portfolio of algorithms, right? So that is, if you use all the algorithms, what's the best performance for that particular graph coloring problem? But if you use that subset of algorithms, what's the best performance? And the difference is, the performance loss, kind of. So that's a performance deterioration. And when you get the performance deterioration, you want to look at the upper tail of it. Right? Because, of course, getting the mean and everything, it will reduce the upper tail. So you want to see what happens to, what is the upper tail like? What are the big values like? So for the graph coloring example, we compared the strong IRT is the green one, and that is our portfolio here using IRT. And these two are other two portfolios. So one is by using Shapley values, and the other one is taking the best on average set of algorithms. So when we look at these, the performance deterioration for the IRT portfolio is lower for this example. So that is the IRT. That's the IRT framework. The IRT framework. So just to go through all the things here, the green ones are the process parts, and the blue blue boxes are, it's part of the process, but you get some output as well. So we have the performance data, and then using that, we fit an IRT model. And from the IRT model, we get algorithm and dataset metrics, which is an output, but it's still in the process, because from the dataset metrics, the dataset difficulty values, we feed the smoothing splines. And then from the splines, we can get the algorithm strengths and weaknesses. It's part of the process, but now you can look at the strengths and weaknesses as well. And then from there, you can build the portfolios and then evaluate the portfolio. So that's the total kind of, the full set of steps. And here's another example from the ASLib data repository. So this is one of the constraint satisfaction problems that they have. They have all these repository of performance data. And so these are the curves that we get. This is CSP Minisync in done in 2016. So these are the performance curves, the latent rate curves. And look at them. They're all over the place. You have one going up and then coming, then coming down like that. So going up, that part is a little bit anomalous, because as the problems get more difficult, those three algorithms, they're going up, but then going down again. And then we can see the strengths and weaknesses, like, you have these big strengths of that particular algorithm, which is, I think, is MZN Gurobi free. And for easier algorithms and for more difficult ones, you have one of these other algorithms. I think this is, this LCG glucose UC free. And then you have these weak algorithms as well. So you see the strengths and weaknesses. And then again, we can, plot the performance deterioration. We see that AIRT has lower performance deterioration compared to other baskets. And then we can also look at what is, if you choose the weak portfolio. In the weak portfolio, as you increase the number of algorithms, what's the proportion of best algorithms? Again, AIRT has a lower proportion of best algorithms in the weak portfolio. So the weak portfolio is the algorithms that we should kind of be thinking of avoiding. They're the not so great algorithms. So, but if you just took taking the on average performance and you take the bottom set, then that doesn't really give much, whereas AIRT does. Now, it's not the case that AIRT performs well for all of them. This is an example where AIRT doesn't perform that well. So this is a SAT11 individual problem set. And here, when we look at this performance deterioration graph, AIRT has the highest performance deterioration compared to the other two. Of course, the best algorithm proportion in the weak set is still lower, but here AIRT is not doing so well. But here's the other thing. All the curves look kind of really similar here. Right? All of them are similar compared with this one where the curves are like, doing a dance. Here you have everything going, everything going just down like that. So the curves are really similar because we believe that for when they did SAT11, they have pre-selected the good algorithms for SAT11 because the authors of ASLib, they're very much into SAT problems and the SAT optimization problems. They're doing a lot on that. So there are so many algorithms, but they've kind of pre-selected some of the good ones. So I think this is more a case where when you've already pre-selected, IRT can't add a lot to it, right? So IRT generally performs well when the set of algorithms, when you've got a diverse set of algorithms, because in a way it ties back to the basics. IRT in education, if all the questions were really good and discriminative and difficult in similar ways, you don't really need IRT to select the more discriminative questions. It's like, you know, when you first go, you've got heaps of questions, and, you know, some of them are discriminatable, some of them are super hard, and, you know, some of them don't discriminate at all. All those questions, if you have a lot of them, then IRT can add a lot. So it's the same for the algorithm evaluation. If you have a really diverse set of algorithms, then we can then the AIRT performs well on such examples. So in summary, we use the IRT framework to visualize the strengths and the weaknesses of algorithms, and we can also use it to select a portfolio of strong and weak algorithms. And of course, we can understand more about algorithms as well in terms of anomalousness, stability, and the difficulty limit. And I haven't spoken about the diagnostics. We have some diagnostics to, you know, just to see if the models are actually doing well. And we have an R package on a CRAN, it's called AIRT. And we have the preprint where there are more applications included. And thank you very much.